In this video, we are going to go over some different enthalpy change definitions that we need in order to start talking about different energy cycles within energetics itself. So we're going to start with the definition for the standard enthalpy change of atomization, or delta H naught of AT. This is the enthalpy change when 1 mole of gaseous atoms are formed from an element under standard conditions. So it's always an endothermic reaction, so the values are always a positive value. And some examples are shown here. So we're taking 1 mole of gaseous atoms and we're forming that. So it's almost like a formation type equation, but a little bit different. And then we're forming it from the element in its standard conditions. So in this example here, we've got a half H2 reacting to give 1 mole of H atoms. That has an atomization enthalpy of plus 218 kilojoules per mole. And 2 more examples here. So we're going from a half Cl2 to Cl atoms. And then we're going from solid sodium to gaseous sodium. And you can see that all of them have positive delta H values. The next one we have is ionization energy. So this is the enthalpy change that occurs when an electron is removed from an atom in the gaseous state. It is also always endothermic. And we can have successive ionization energies. So for example, we could take M and react to give an M plus electron. That would be the first ionization energy. The second ionization energy would be taking that positively charged ion and removing another electron to make the 2 plus ion, and so on and so forth. So an example might be if we're taking sodium in the gaseous state. So this is from maybe atomizing sodium and forming sodium ions and an electron. So this has a delta H of plus 496 kilojoules per mole. Now we also have electron affinity. So this is the enthalpy change that occurs when an electron is added to an isolated atom in its gaseous state. A couple things here. The first electron affinity is always exothermic, so it always has a negative value, while the second electron affinity is always endothermic or has a positive value. So the reason for this being, in the first electron affinity, it's favorable to bring an electron from infinity, so out there, to where it feels the attractive force of the nucleus in an atom. The second electron affinity, though, becomes unfavorable to add an electron to an ion which already is negatively charged, and that's because negative charges repel each other. So this first electron affinity here is a negative value, and so we're taking X, we're adding an electron to make an X minus, and then if we try to add another electron to X minus, it gives us X2 minus, and that would have a positive value. So an example might be chlorine atoms with an electron to make the chlorine ion, and you can see that first electron affinity there is a negative value. Now you can find these values, the first ionization energy and electron affinity values, from various different sort of data tables. So this periodic table here gives first ionization energies up in the top left corner here. It gives the first electron affinity and the second electron affinity values in the top right-hand corner. So you can see, for example, with oxygen, the first one's negative, the second one's positive. Same here with sulfur, and so on and so forth. Okay, so you can get those values directly from a periodic table. The last enthalpy change we need to look at is something called the lattice enthalpy, or delta H naught and then lat. for short. So this is the enthalpy change when 1 mole of an ionic compound is broken apart into its constituent gaseous ions under standard conditions. So essentially, this is the enthalpy change associated when we break apart a ionic compound, so an ionic lattice. Remember, they have a lattice type structure. Now, in terms of this sort of definition, if we're going from ionic compound to gaseous ions, it's always endothermic because we are breaking forces of attraction. In this case, we're breaking the ionic bond, which is really just an electrostatic attraction. So something like lithium chloride in the solid state, breaking it down into its ions, lithium ions and chloride ions in the gaseous state, would have a positive lattice enthalpy of plus 864 kilojoules per mole. Now again, there are data tables that have all of these different sort of values for various different ionic compounds. Kind of the way you would read this is you would come and find your metal here, and then you'd find your non-metal. So if we're looking at sodium fluoride, it'd be plus 930 kilojoules per mole. And then some of the other substances are listed down here, and you could take a look and find those values. Now remember, lattice enthalpy is the result of electrostatic attractions between oppositely charged ions in a giant lattice. So that means the greater the electrostatic attraction between the ions, the more energy that has to be supplied to break apart the lattice. So that means that lattice enthalpy does depend on a couple of different factors. It depends on the charge, and it depends on the ionic radii. So with the charge, the higher the charge on the ions, so if the higher the charge, the more strongly they're going to attract each other. That means that you're going to have a higher lattice enthalpy. Lattice enthalpy is also larger for smaller ions. So as the ionic radius goes down, the delta H of lattice will go up. But the ionic radius itself is kind of more of a minor factor than the charge. So the effect of the charge causes a larger change in the lattice enthalpy than do size variations. So if we're kind of thinking about this in terms of melting points and boiling points, a substance that has a high lattice enthalpy would also have a high melting point because melting points are going to depend on the forces of attraction between the ions. So this would have a higher melting point than something that has a smaller lattice enthalpy. So those are various definitions of different enthalpy changes that are related to energy cycles. That's it for this video. We'll see you in the next one.